All right, here we have an example pencast for problem 21 in homework set 2. So the problem reads, we have two 2 centimeter in diameter discs that face each other that are 1 millimeter apart. So let's draw this setup. Okay, so here are their 2 plates. This separation is 1 millimeter. And then this diameter equals 2 centimeters. Okay? And then as we read on, it says that they are charged of plus 10 nanocoulombs and minus 10 nanocoulombs. So we'll call this the minus side and this the plus side. Okay, so now question or part A wants to know what is the electric field between the plates. So we can write down the equation for the electric field. Okay. So before we can choose the equation, actually we need to have notice one thing in particular. So if you see here that these plates are 2 centimeters long, but the spacing is only 1 millimeter, this means that the dimensions of these plates is much larger than their separation. So this means that we're in the scenario where we have a parallel plate capacitor. Okay, so this means that if we need the electric field, we have the equation for this is Q over A epsilon naught. Okay, so this is the equation that we want to use. So now let's write a list of knowns. So we know what Q is. It equals 10 nanocoulombs, which is 10 nanocoulombs. 1 coulomb is 10 to the 9 nanocoulombs. So this is 10 to the minus 8 coulombs. And then we know the diameter D equals 2 centimeters, which is 1 meter per 100 centimeters, so 0.02 meters. Okay, so if we know the diameter and the charge, we know everything we need to solve for the electric field. So this is going to be Q over pi r squared epsilon naught. So where this pi r squared came from is because we want the area of a circular plate. So the area of a circle is pi r squared. So this is 10 to the minus 8 coulombs over pi 0.01 meters squared. So recall that this is the radius, not the diameter. So if we want the radius, we need to take half of the diameter. And then epsilon naught, 8.85 times 10 to the minus 12 c squared per Newton meter squared. Okay, so if we plug all this into our calculator, we see that we get 3.6 times 10 to the 6th newtons per coulomb. Okay, so the important thing to remember here is that if we look at our setup, we made this the negative plate and this the positive plate. That means the electric field is going to point to the left. So point in the negative x direction. So this is actually going to be the electric field, and it's going to be in the negative x direction. Okay, now part B. In part B, we want to put a proton at the tip of this negative plate and then launch it at the positive plate, and we want to see how fast we need the initial velocity be so that the proton just reaches the positively charged plate. Okay, so basically we want to find V initial. So again, let's write down our knowns. So we know the charge of the proton, QP, is 1.6 times 10 to the minus 19 coulombs. We know mass of the proton, 1.67 times 10 to the minus 27 kilograms. We know the electric field equals minus 3.6 times 10 to the 6 newtons per coulomb. We know delta x is going to be 0.001 meters, because that's how far it's going to travel before it stops. And we know the final velocity equals 0 because it just reaches the plate. So what are our unknowns? We don't know the acceleration, and we don't know initial velocity. Okay, so if we know the electric field, and we know the mass, and we know the charge, that means we can find the acceleration using Newton's laws. So we know that force equals mass times acceleration, and the force from an electric field equals QE. So we can solve this for acceleration, and the acceleration is going to be equal to QE over m, which is going to be 1.6 times 10 to the minus 19 coulombs times minus 3.6 times 10 to the 6th newtons per coulomb, and then divided by 1.67 times 10 to the minus 27 kilograms. And this is going to give us acceleration equals minus 3.45 times 10 to the 14 meters per second. Okay, so now we know the acceleration. So we know v final, we know delta x, and we know acceleration, and we don't know the initial velocity. However, we also don't know anything about time. So if we look back to our kinematic equations, all but one equation deals with time. So that means the equation we want to use is the one that does not deal with time. And that equation looks like v final squared equals v initial squared plus 2a delta x. So this is the equation we want. Notice that there's no time, but we know delta x, we know a, and we know v final. So this means that we have 0 equals v initial squared plus 2a delta x. So we can solve this for v initial equals square root of minus 2a delta x. So then down here we can finally plug in the numbers. So this equals minus 2. The acceleration is minus 3.45 times 10 to the 14 meters per second, and delta x 0.001 meters. And this is going to give us a final answer of an initial starting velocity of 8.3 times 10 to the 5 meters per second.